Okay, so from this point onwards, I'll just start layout design. Sorry, layout design is a process to develop a layout of placement and routing of components in order to prepare a PCB for an electronic circuit. So first of all, it gives us a mechanical dimension that is available. Okay, this is my PCB size. Then what else is involved here? Placements. All the components required to be placed with with highest uh, skill, because placement is required. This is very important. Placement of component on a PCB. It is not like we should not keep randomly anything anywhere. Then the system will go wrong. Placement is very much important. It's a really skilled job. And then routing, that is another skill job, that it is not just we have a PCB, we have 50 components, we have placed quickly or suddenly somewhere, then we have routed them somehow. No, we will see what some of the tips what we can keep in mind while designing a PCB. So the problem, what I said, no, that cannot be done, like placement routing cannot be done. Why? Because of noise and EMI EMC issues. So this looks a very small slide, just few words, noise and EMI EMC, but this has become a biggest problem in industry for electronic engineers. They have to deal with noise every day in every system. They have to deal with EMI EMC issues in every system. This is very important topic. In fact, this is altogether a different subject to study. So EMI means electromagnetic interference and EMC means electromagnetic compatibility. Interference means A is disturbing B. A electronic system is disturbing any other electronic system B or any other circuit. So it is interfering. So this is interference from A side. If B is getting affected, it should have uh, its own safety shielding or its own safety features, so that it should not get affected by other devices. So if we have in old mobile phones and some of the old speakers, if we remember, we have observed noise. Sometime when phone rings, nearby speaker start tuduk 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 tuduk. Sometime very old, like 20-25 years back, if there is any aeroplane flying on the top, then TV screen, you might see the disturbance in the TV screen. All these things are kind of example of electromagnetic interference and compatibility. So that system is not really very compatible in terms of EMC. So that gets disturbed. Nowadays, in advanced speakers and advanced mobile, you will find such problems are like omitted, because they have arranged them in such a way that it will not easily get disturbed by a nearby devices. So this is not a problem between device and device. This is a big problem within a system as well. What I mean, like we have seen many circuits: sensing circuit, controller circuit, power circuit, driver circuit, communication circuit within a system. If power circuit is disturbing controller circuit, controller will not work. Resultantly, it will not allow power circuit to work correctly. If a driver circuit or power circuit is disturbing sensing, then sensing will not work properly. Resultantly, the whole system will not work. So what kind of noises we can observe? Uh, why that happens? We all have studied this Biot-Savart law. I kept it here just for one understanding. Every current carrying trace or every current carrying wire makes a difference. How we have studied that when a conductor is carrying a current, it will have a magnetic field around it, right? That is maybe defined by B, magnetic field density. If 10 ampere current is flowing, then it will have some magnetic field. If 100 ampere current is flowing, then it will have stronger magnetic field. Did we thought about if a milliampere is flowing through that conductor. Still, will this have any kind of magnetic field? This law says yes. Even if microampere current is flowing, that will produce some magnetic field. We cannot say it is zero. There will be some magnetic field. All these magnetic fields are playing important role in the circuit design. Kind of noise we can observe. This is a system I was working many years back. So we have seen pulses, and in the books when we study power circuit or when we talk about pulses, gate pulses, we usually see that. This is the gate pulse, practical gate pulse. This should not be like this. Like, it should be smooth, smooth rising, then smooth falling. What is this happening? And this is happening in one point of the circuit, and you can see another any other point of the circuit, any other node of the circuit is getting disturbed. It should be like straight line, but whenever this noise is generated, there will be a noise in another circuit also. When this noise is generated in one part, then that noise is just reflecting, or it is also inducing some voltage or producing some current in another circuit also, which is just, it might not be connected to each other physically. They are just close to each other. Still this noise is affecting the other circuit. This is another example. This circuit is at rest. Nothing is connected to that. Still, if we see no voltage and no operation is happening, still when we connect a probe, we see some noise across that. So that circuit can also become a live circuit if there is anything nearby. You know why? Because we know uh, E is equal to uh, E is directly proportional to d phi by dt. If there is any change in the flux nearby device, so that some EMF will induce in another circuit. Another kind of noise, you can see one system, these are two different signal, okay, two different points where these noise is observed. One is yellow one, so this the red one is having some noise, so, resultantly similar kind of noise is also induced in another point of the system. Both of them are measured here. Such kind of noise in a switching circuit is very obvious to be observed. They are like very common, but they are very problematic as well while designing. So disadvantages of noise, I have made these points like underlined because we need to understand they are really very important. What all goes wrong? First of all, your control gets affected. Maybe your control circuit will not work. All of our programming, all control loop design, Bode plot, and this, that, everything, or MATLAB simulation, everything is done perfectly. Everything is fine. Still, it will not work. It will be affected. Sensing is perfectly fine. Every device, every part of the sensing circuit is very good, but still, it doesn't give expected performance. Performance of components get affected. Other components, like there may be some actuating circuits or anything, their performance will be affected. Output of the system is distorted. We have done MATLAB simulation, other kind of simulation, everything is working fine, no problem in the simulation. We have made a circuit of the similar structure, same circuit is made in hardware, then we see, oh, there are, what is this happening? System is completely, output is distorted. And this is not only disturbing the circuit. Suppose somehow somebody has made it work, still sometimes meeting standards becomes difficult. There are several electronic standards, one product has to pass those standards. Some of them are EMI EMC related, some of them are uh, not really EMI EMC related, but those standards should pass. So system is working, but it is not meeting the standard. People have to work on them. People have to reiterate system. They have to redesign the system. Even after correct circuit configuration and control design, system fails. So I give you one my own experience. I was working on a 3.3 kilowatt system. First inverter when I have made, first design of that circuit. Every component was designed or maybe I purchased and put on the PCB based on 3.3 kilowatt. First time, first iteration worked only for 20-22 watts. System is rated for 3.3. All the components are based on 3.3 kilowatt, but that system was only producing 20-22 watts. After that, if we increase power, system doesn't work. In the second iteration, we could get 100, 200 watt. In third iteration, we could get 1000 watt. And after sixth iteration, we could get a very smooth, correct output without any problem. So it took like six iteration for a system, for a PCB to to sort out all these design related issues. Components are still same. Everything was same. It is just placement and routing of those components which were making problem in control and sensing. These points are underlined because these are the major issues we see in hardware design. What is behind all this misery? Magnetic field and electric field. That's it. These are more dominant as voltage and current of the system increases. So what I mean by this, we sometime when we design a simple electronics circuit, like signal electronic, like I will classify signal electronics and power electronics. Okay, so a small circuit is small electronics when the power rating is just 1 watt or couple of watts, they are not really processing any power. So those circuits, signal electronic circuit, there is no sometime a beginner can start to design some circuit and he can design it and it works. That does not create more problem because voltage and current rating of that is very small, 3.3 volt, 5 volt, 12 volt, and current range is also like in milliamperes. Very hardly it goes to 1 ampere or 2 ampere. But when we talk about power electronics, when voltage is their range is in hundreds or can also go to thousand, when current rating is like in 100 amperes, tens of ampere, hundreds of amperes, or maybe sometime goes up to 1000 ampere, then the problem is really big problem. Then we have to really take care of the system. Same electronic circuit, if designed for 10 watt, same just scale it up in terms of all the components, everything else, but it may work for 10 watt, it may not work for 1000 watt. Same configuration, same circuit diagram, same everything is same. It may not work for 1000 because we need to take care of design, placement, and routing. One thing I would like to, we know all the wires, all the conductors, they have resistance. Here nothing is like superconductor. We on normal temperature, every conductor, whether it is copper or silver, anything, they have some resistance. Similarly, every conductor or every trace has inductance also. So that inductor value of a simple wire or simple trace, flat trace, that can be calculated using this formula. And in approximately this is the range, and in nanohenry, if width is this much, 0.25 mm, or in inch if it is 0.01, thickness is 0.07 mm, then approximately we'll get 10 nanohenry of inductance per centimeter. Okay, one example of radio frequency antenna I tell you. This is size of this PCB is approximately 1 inch by 1 inch. Okay, and they have made an antenna within the PCB. So this this uh, up down pulse kind of structure we see here. This is nothing but an antenna. This is the utilization of this structure. They created this intentionally. This is called an RF antenna we get in the market, and this is the antenna. And the PCB itself, this is the trace. So if such a small trace or such a small strand like current is almost just voltage, and these ratings are very small. If we put 1000 volt in a trace, or it is carrying like hundreds of ampere current, don't we think that it will radiate something with very high intensity? It will. So that's just to put an example how a simple trace of PCB can behave like an antenna, which is really used in communication in practice, RF communication. Okay, so let us take an example of a buck converter as well as a full bridge converter. Okay, I'll just take my stylus. 1 second. Some interesting things I would like to present here. Okay, so when we talk about a buck converter, we see, okay, we have an input source, voltage source, we have a switch, right? We have a diode, we have an inductor and a capacitor. That's it. Is that really it? Don't we have any other thing here? If we go for a hardware design, there are many other things apart from these components what we see on the screen. For a full bridge, we say, okay, there are 4 switches, that's it. This becomes full bridge. No, let me take what happened. Okay, 1 second. Yeah, I'll take a pen here. Apart from these components, we have many other components present in the circuit. As I said, each trace, each conductor is having an inductor. This line may have an inductor and also a resistor. Oh, sorry. Is that visible? Screen is still visible?
So now it's okay.
Yes, sir.
Okay, okay. Thanks. So this trace can also have an inductor. This trace can also have an inductor. Though the value is in nanohenry, but it will have. This trace will have an inductor and resistor. This trace will also have an inductor. Not only inductor and resistors, we will have capacitance between these 2 points. We don't know. We will have capacitance between these 2 points. Though the value is in picofarads, or maybe if very large, then it can go up to nanofarad, but we have capacitances between any 2 points. Between this and this, we may have a capacitance in hardware. Here also in full bridge, we may have some inductance in the trace, some resistance, value in micro ohm or maybe in milliohm. But all of these traces are having some inductance or some resistance. This will have some inductance. There will be a capacitance between these 2 points. There can be a capacitance. There will be a capacitance between these 2 points. What is the basic principle of capacitor? We have two conductors. They are separated by dielectric. That could also be air. This is a conductor. This is a conductor. It will create a capacitance. So this is a conductor. Here, let's say this point, this is a conductor. They are separated through air. There will be a capacitance. There can be a capacitance between this. There can be a capacitance between these 2 points. So this is all we have, but we don't know the values of these capacitances and these inductance and these resistances. They are called parasitic. In fact, if we have buck converter and boost full bridge converter here, they are close to each other, or they are like kept side by side. There will be a capacitance between these two terminal also. Huh? There will be a capacitance between this point and this point. All these unknown, unwanted components we don't know. We just know about S1, D1, LC. We just know about C in S1, S2, S3, S4, LC. Apart from these components, we have several hundreds of components within the circuit. They will have very small value, yes, but they are there. These are called parasitic. They create problem in hardware design. So let's see some of the things what we can avoid or we can reduce problem produced by these things, how we can reduce. So these are the critical traces. Critical traces means the critical lines which can create problem in a switching circuit. Okay, what I mean by that, I'll just explain this. Here we have this buck converter. So when this switching will happen, the inductance of this trace and this trace, we know uh, we cannot interrupt current through an inductor, right? That is in fact uh, applicable here also. If it has a parasitic inductance, this line as well as this line and also this line. If we suddenly switch off, then the current which was flowing through these inductors, we cannot interrupt it. What will happen to that? That energy or that current, it will oppose the sudden interruption, and that energy will combinedly appear across the switch when the switch is getting turned off. So here we see some V in voltage plus some other delta V. This delta V in we know, see, and switch is on off, then this V in will appear here, fine. But what about this delta V? What could be the value of this? If suppose this is 12 volt, delta V can be zero point 0.1 volt, this can be 1 volt, this can also be 10 volt, and this can also go to 100 volt, and this can also go to probably 250 volt. So we have selected a device as per 12 volt voltage, but it is carrying 100 or 250 volt. It will like blow off. It will not work, right? This is not like maybe mind blowing, but it is that this delta V can be 10 times or 15 times or 20 times more than the supply voltage. What a big problem. So if these red marked traces, if they are reduced, they are the critical part, because the inductance of this will add up to this inductor and it will have free will path. That's okay. This inductance of capacitor and this trace, fine. So this will make a kind of LC circuit, and whatever energy is stored in the inductor, that will somehow stored in the capacitor. This inductance and then other parts will go to load. This red part is the critical part. We generally call this a switching loop. This is the switching loop of the circuit. This loop should be as small as possible in order to reduce these inductances. And like uh, resistors are not really affecting such type of phenomena. They will have power loss, but these inductances are really critical. Similarly here, if we have inductor here, we have resistors here, so it is fine if the switch is off or there is no power, so they will transfer their energy to capacitor. This loop is not problematic. But when switch is off, Somebody wants to say something?
Oh, sorry, sir. Sorry.
Oh, that's okay, no issue. Okay, so this is the critical trace. Why? Because when switch is turned off, then the inductance of this and the energy stored in this inductance that will appear across the switch like a large spike of voltage. Here also, when this switch is turning off, that will create a large spike across it because of these inductances. These red marks are the critical traces. Inductance of this path may not affect because anyway we have another inductor. So this inductance will add up to this inductor and resultantly it will have some freewheeling path whenever we are operating, like turning on and off. But red mark are the critical traces. So we should reduce the parasitic effect of these traces. Okay. They are called, these loops are called switching loops, as I said here in buck converter. Whenever the switching device is involved in the loop and it is turning on and off, what generally happens in SMPS, switch mode power supplies, or any kind of inverter or anything related to power electronics, it will have a device which is turning on and turning off. That loop is called switching loop. Okay. So how we can reduce these stresses? First of all, whenever we are designing a circuit, we need to identify what are the critical traces.